Now let's discuss about the first Brillouin zone, the behavior of phonon dispersion inside the first Brillouin zone. We have already discussed that the range of k that is physically significant is within the first Brillouin zone, that is minus pi over a to pi over a. This is the significant range. And if we take the ratio of displacement of two successive planes, that is if we take us plus 1 over us, if we calculate this quantity, we will find u exponential of I s plus 1 ka over u exponential of I s k a. This is nothing but, you can clearly see, exponential of I k a. So, the range minus pi to pi for the phase Ka covers all independent values of this quantity, of this exponential. The range of independent values of k is specified by minus pi less than equals Ka less than equals pi. This is the range of independent k, that means minus pi over a less than equals k less than equals pi over a. This is the significant range, and this is the first Brillouin zone for the linear lattice. That means the Brillouin zone for the lattice that we have is the same as the Brillouin zone for the lattice vibration. Now let's discuss the group velocity. You know that group velocity is the velocity at which energy propagates in a wave, and energy is one of the most important physical quantities that in every context of physics we need to understand. So the transmission velocity of a wave packet is the group velocity, and the group velocity is given as d omega dk. Vg denotes the group velocity, this is d omega dk. In 3-dimension, group velocity is given as the gradient in k space of omega, which is a function of k. This is the velocity of energy propagation in the medium. With the dispersion relation that we found here, this dispersion relation or this dispersion relation, the same thing actually, the group velocity we have according to the dispersion relation, omega equals 4c over m square root of this quantity sine half Ka, absolute value of this, because frequency cannot be negative. So the group velocity becomes Ca squared over m square root of this times cosine half Ka. Remember, group velocity can have negative sign, there is no restriction, although the frequency could not be negative. So the group velocity is 0 at the zone boundary where k equals plus minus a. that you can readily see. The wave is a standing wave, and we cannot expect any net transmission, because when the wave hits the zone boundary, there is no group velocity, the group velocity becomes 0, so energy cannot flow out of it. So the energy is confined within the Brillouin zone, that we can clearly see from our calculation, and therefore it has to be a standing wave. The energy is not propagating beyond a Brillouin zone. That's something very important that we can see from our calculations. Now let's see the long wavelength limit. The long wavelength limit is given as Ka much less than 1. If we have this limit working, we can expand cosine of Ka as 1 minus half Ka squared. We truncate the series right here, we do not write the next terms, because Ka is much smaller than 1. And if we have this, then the dispersion relation becomes omega squared equals C over the mass K squared A squared. That is all, because it is 1 minus cosine of Ka. So, this is it. If we have this, the result that the frequency is directly proportional to the wave vector, as we can see here, omega square is proportional to K squared, in the long wavelength limit is equivalent to the statement that the velocity of sound is independent of frequency within this limit. Why are we talking about velocity of sound? Velocity of sound moves through a medium by making waves into the medium. That means it makes the lattice vibrate. And in the case of lattice vibration with long wavelength, we can see that omega and K, these two are linear within this approximation being valid. And therefore, we can say that the velocity of sound is independent of the frequency of that sound in the long wavelength limit. Therefore, the velocity can be given as omega over K. This is the velocity of sound, this is the phase velocity of any wave, and this remains a constant independent of frequency within a certain range of frequency, that is large wavelength, low frequency limit. This is exactly the result obtained from the continuum theory in elastic waves, continuum theory of elastic waves. Now let's find the force constant and see how it is, let's see how the force constant is found from experiment. In metals, the effective force may be quite long range and carried from ion to ion through the conduction electron sea. Interactions have been found between planes of atoms separated by as many as 20 planes, while in our assumption we have considered only the nearest plane interaction, nothing beyond. The generation of the dispersion relation to, if we consider p number of nearest neighbor planes, it is found from empirical observation to be omega squared equals 2 over m sum over p greater than 0 Cp 1 minus cosine of pKa. So, what are we talking about? We are talking about more than nearest plane interaction, more than nearest neighbor interaction, and empirically this has been found to be the dispersion relation, provided P is the number, that is index of the plane that we are considering here. Now, if we solve for the interplanar force constant Cp by multiplying both sides with cosine of RKa, where r is an integer, and then we integrate over the range of dependent values of k, we can do that by in the following way. We multiply it with cosine of RKa and integrate over the range of k, that is the first Brillouin zone. Integration from minus pi over a to pi over a of dk omega k squared cosine RKa, r is an integer, this quantity equals 2 times sum over p greater than 0 Cp, this is the interplanar force constant, integration over the range minus pi over a to pi over a dk 1 minus cos pka cos r ka. This is what we get, and this is twice pi cr over a. The integral vanishes except for p equals r. This integral vanishes if p not equals r. So, the only term that survives is twice pi cr over a. This is the only term that survives. With this, we can write Cp equals minus m a over twice pi integration from minus pi over a to pi over a dk omega k squared cosine of p k a. So, this Cp gives us the force constant at range Pa for a structure of monoatomic basis. This is the situation valid for metals. For non-metals, whatever we have considered earlier, that is nearest plane interaction, is fine. For metals, it is not fine. So, for metals, this kind of a form of the interaction constant, the force constant, is observed empirically.